Exponential functions. Recall that a linear function has a constant rate of change. That is, the outputs change by the same amount for each unit increase in the inputs. An exponential function has outputs that are multiplied by a fixed number for each unit of increase in the inputs. Let me show you an example of this. Comparing these two functions, if I have y equals x plus 7, making a t-table, putting some inputs in, I have 0 plus 7 is 7, 1 plus 7 is 8, 2 plus 7 is 9, 3 plus 7 is 10. The rate that these outputs are changing by is 1. We're adding 1 every time. The rate of change being your slope. If I had something like y equals 2 to the x, and I make the same t-table with the same inputs, quite a different thing happens with the outputs. 2 to the 0 is 1. 2 to the 1 is 2. 2 squared is 4. 2 cubed is 8. So we're not adding the same amount every time on the outputs. In fact, we are multiplying by a fixed number, and that number here is 2. 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 8, and so on. And that's what makes this function exponential. If b is a positive real number with b not equal to 1, then the function f of x equals b to the x is an exponential function. The constant b is called the base of the function, and the variable x is the exponent. Example 1, transformation of graphs and exponential functions. I first want us to graph y equals 2 to the x by using a table of points, not just by putting it into our graphing calculator. So let's make a table and decide what values could x hold. We could use negative numbers, 0, and positive numbers. So let's put a good mix of these numbers in our t-table. 2 to the negative 3 is going to be 1/8. 2 to the negative 2 is 1/4. 2 to the negative 1 is 1/2. 2 to the 0 is 1. 2 to the 1 is 2. 2 squared is 4, and 2 cubed is 8. So when we go to graph this, we can see at negative 3, we are at 1/8. It's very close to the x-axis. At negative 2, we're at 1/4. At negative 1, we're creeping up to 1/2. At 0, we've made it to 1. 1, 2, 2, 4, and by 3 we're already up at 8 off my graphing grid that I have shown. So we see that this will increase, continue to increase without bound to the right. And to the left, what's going to happen? Even if we would put something like a 2 with an input of negative 5, that's 1/2 to the 5th, which is 1/32. It's very small. It's just going to continue to get closer and closer to that x-axis. But you know, it never reaches it. There's never a negative enough exponent that I could put on that causes the function to have an output of 0. So what we would describe there is a horizontal asymptote, and that horizontal asymptote is y equals 0. In other words, if you look at this graph way out where x becomes more and more negative, a larger and larger negative number, the graph basically looks like the line y equals 0. It never really gets to it, but it is approaching that, getting infinitely close to it. Now, what are the intercepts? I see one right here. That's the y-intercept of 0, 1. We've already said that the graph will never reach, it'll never reach 0. So on the x-intercept, we have no x-intercept. What is the domain and range of this function? We've already talked about the domain. We said that x could be any exponent. So the domain is going to be from negative infinity to positive infinity. For the range, we have a variety of outputs, but they'll always be greater than 0. Okay, we get infinitely close to 0, but we never really touch it. So we're going to put a parenthesis on that. Okay, now let's go ahead and go to the graphing calculator. On the graphing calculator, graph each of the following functions on the same axes as y equals 2 to the x. So I have here 2 to the x, and see what that looks like. Looks nice. And let's put in this function y equals 2 to the x minus 1, and graph that. And what has happened is that this has shifted right 1 unit. You can see even in the table, an input of 1 gives us 2, but it takes an input of 2 to give us a 2 on the second function. An input of 2 gives us a 4, but it takes an input of 3 to get us an output of 4 on the second function. So every x has to be 1 more. It's been shifted to the right 1 unit. With y equals 3 plus 2 to the x, let's see what that looks like compared to our original function. And you can see, especially this is apparent on the left side, this has been shifted up 3 units. You can see on the table of values, as x goes to negative infinity, this value is approaching 0, and this value is approaching 3. So this is a graph that has been shifted up 3 units. Let's try this last function. It's 2 exponent of negative x. And I graph that. We get this graph that is no longer increasing, it's decreasing. Generally, when people say something is exponential, they think that it's increasing greatly. And that seems to be the word that people use, but we can also have an exponential function that is decreasing, and these are the types of things that we use for decay models. And so what this has had done with the graph is reflected it over the y-axis. You could fold your graph on that y-axis, and those two graphs would lie on top of each other. Exponential growth models. Exponential functions can be used to model growth in many different applications. Whenever the base b of y equals a times b to the kx is greater than 1, and a is greater than 0, and k is greater than 0, then the exponential function is increasing, and it can be used to model growth. Example 2 is an excellent example of the exponential growth model. Suppose that inflation is predicted to average 4% per year for each year from 2012 to 2025. This means that an item that costs $10,000 one year will cost $10,000 times 1.04 the next year. In other words, we're paying 100% of what it cost before plus another 4% tacked on. The next year it's going to be $10,000 times the 1.04 from the last year, and then we're going to multiply that amount by another 1.04. Well, a more concise way to write that would be $10,000 times 1.04 squared. And so on. So if we go for another year, it'll be $10,000 times 1.04 times 1.04 times 1.04, or in other words, 10,000 times 1.04 to the third. The next year would be 10,000 times 1.04 to the fourth. So write the function that gives the cost of a $10,000 item t years after 2012. We're going to have f of t equals $10,000 times 1.04 to the t, where t is the number of years after 2012. Graph the growth model found in Part A for t equals 0 to t equals 13. So let's go to y equals. We'll clear out our previous functions. This will be 10,000 times 1.04 with an exponent of x, and they want us to graph it from t equals 0 to 13, so we're going to have our x min as 0 and our x max as 13, and we'll do a zoom fit to see that in a nice window for the years 0 to 13. Now if an item costs $10,000 in 2012, use the model to predict its cost in 2025. Well, the thing that they've given us is the number of years after 2012. For 2025, t is going to be 13 years after the year 2012. So one way to find this would be to hit trace and then enter the number 13, and your output shows there as $16,650.74. So that is the cost of a $10,000 item in the year 2025. The next example is on sales decay. It pays to advertise, and it's frequently true that weekly sales will drop rapidly for certain products after an advertising campaign ends. This decline in sales is called sales decay. Now suppose that the decay in the sales of a product is given by S equals 1,000 times 2 to the negative 0.5x dollars, where x is the number of weeks after the end of a sales campaign. Use this function to answer the following. What is the level of sales when the advertising campaign ends? I think it's good for us to backtrack now and decide what our x and y is for this function. The x is the number of weeks after the end of the sales campaign. So x is number of weeks after that campaign. And our y is the variable s, and that's the dollars in sales. So what is the level of sales when the advertising campaign ends? Which of these things have they given us? Which thing are they asking for? They're asking for the level of sales, so it means they must have given us the number of weeks after the campaign. Well, when the advertising campaign ends, then the number of weeks after the campaign would be 0. So we are taking 0 as our input in place of the x, and that makes that exponent 0. 2 to the 0 is 1, times 1,000 is $1,000. So the level of sales when the advertising campaign ends is $1,000. Now, what is the level of sales 1 week after the end of the campaign? So for us there, x would be 1. So we're simply going to put this into the function. There we go. And we can put that into the calculator. 1,000 times 2 with an exponent of negative 0.5 times 1. And we have a sale level of $707.11. Next, they'd like us to use a graph of the function to estimate the week in which sales equal $500. So let's go to y equals, put our function in, and let's set our window. For our window, we can start with 0, and we can see after just 1 week the sales have dropped drastically. Shouldn't take long to get it to $500. So let's put in a 5 so you can get a good piece of the graph to view. And where is it that we have sales equal to $500? The number 500 that they're giving you is an S, or the y. So what we can do is put another function in where y equals 500, meaning that the sales in dollars is 500. And graph. Definitely see the intersection of those graphs. So I'm going to calculate the intersection. And it's at just 2 weeks. The sales are down $5 to $500. So 2 weeks is the time. Now, according to this model, will the sales ever fall to 0? Well, let's look at our table. At our table, set our table starting at 0 and scrolling down. Our sales do decline quite a bit, right? But according to the model and from our knowledge of these exponential functions, the sales will never fall to 0. They'll get very close, but they will never fall to 0. A quick discussion on the number e. The number e is an irrational number. It's called the Euler Constant. And many real applications involve the base e. The number e is an irrational number with a decimal approximation to 9 places right here. This is not something that you need to memorize. In fact, it's in your calculator already. If you go to your calculator, you'll see second natural log right here is the e to the x function. So e to the 1, it prompts you for an exponent, and there you go. To so many decimal places is there. Of course, this goes on without, the number of decimal places goes on without bound. We can see this used here, the future value S of an investment of P dollars for T years at annual interest rate R, compounded continuously, is given by S equals PE to the RT. A lot of people like to call this the PERT formula because it looks kind of like PERT, like the shampoo. Easy to memorize. Example 5 is growth of an investment. If $10,000 is invested for 15 years at 10%, and that's compounded continuously, what is the future value of the investment? So we can fill this in. S is our future value of the investment, and P is that principal of $10,000. E is your Euler constant. Your rate needs to be expressed in decimal form, and time is always in years, so we'll put 15 there. And if they had said something like 6 months, then you would put in a 0.5 or a 1/2 because it's always in years as your unit there. All right, so we'll get this put into the calculator just from the home screen. 10,000 times second, natural log gives us E, to the 0.1 times 15, and that will be $44,816.89 is what that compounds to after 15 years. Example 6 is carbon-14 dating. This looks like an intimidating problem, but really they're giving you a mini science lesson up here about what carbon-14 dating is, and they're defining what the variables in the formula mean. So let's read through this. During the life of an organism, the ratio of carbon-14 atoms to carbon-12 atoms remains about the same. When the organism dies, the number of carbon-14 atoms within its carcass begins to gradually decrease, but the number of carbon-12 atoms do not. So they can be measured to determine how many carbon-14 atoms were present at death. The number of carbon-14 atoms in an organism when it is discovered can then be compared to the number present at death to find how long ago the organism lived. The ratio of the present amount, which is Y, of carbon-14 to the original amount, which is Y sub O, T years ago, is given by Y over Y sub O equals E to the negative 0.0001297 T, which produces a function f of t equals Y sub O e to the negative 0.0001297 T. That gives the amount remaining after T years. So your T is years, and Y is your present amount. So here, if the original amount of carbon-14 present in an artifact is 100 grams, how much remains after 2,000 years? Let's go ahead and fill in this function. Y sub O, remember, is your original amount. The original amount of carbon-14 present in an artifact is 100 grams. Then we multiply that by E to the negative 0.0001297 times T. They want to know how much remains after 2,000 years, and that is our T, the 2,000. So this will calculate the amount after 2,000 years. Let's put this into our calculator. So we have 100 times second, natural log to put in our E, to the negative 0.0001297 times 2,000. and I get about 78.5 grams. The next question they want to know what percent of the original amount of carbon-14 remains after 4,500 years. So we can actually use the same function that we had before and just change the 2,000 to 4,500. And it's been then decreased to 58.02 grams. But the question being asked is what percent of the original amount? Well, the original amount was 100. You can even think of that as 100%. And this is the amount that was left. So 58.02 is 58.02% of the original 100 grams of carbon-14. That does it for this section, so go ahead and try the homework and let me know if you have questions.